So in the last lecture, we discussed the relationship between Bayes' rule, MAP, ridge regression. In this lecture, I want to continue this line of discussion of how Bayes' rule relates to the linear regression problem. So let's look at the Bayesian linear regression problem. So again, to refresh our memories, we have the vector y in Rn. This is the vector of responses. And a matrix of covariates, that's n by d, where the ith row of y and x correspond to the ith observation pair yi, xi. And we're not really worrying about whether there's an additional dimension of ones or whether we've standardized the data. We assume that we've pre-processed things in a way such that it works out. We're more interested in the math techniques here. So in the Bayesian setting, we use the following model for this data. We assume a likelihood. We assume that y is generated from a Gaussian with mean equal to xw and covariance sigma squared I. And we then place a prior distribution on the vector w, which is zero mean Gaussian and covariance lambda inverse I. So in this case, the unknown model variable is the vector w in Rd. And we are hoping to learn something about this vector. And so what the likelihood model does here is it says how well the observed data agrees with a particular vector w. And the model prior is our prior belief or our prior constraints that we're going to place on w that we're going to define in advance. So we call this Bayesian linear regression because we've defined a prior on an unknown model parameter or a model variable. And we're now going to try to learn the posterior distribution of the model variable given some data. So again, we saw last time that instead of finding the full posterior, we could find the MAP solution, where we return the maximum of the posterior distribution of w, or equivalently the maximum of the joint likelihood of w, because we saw that the normalizing constant here did not actually impact the location of the solution. Start that over. Okay, so before discussing Bayes' rule in the context of linear regression, we saw last time how the maximum a posterior solution can be found, also called the MAP solution, by finding the value of the vector w that maximizes the posterior. And we also saw that because by Bayes' rule, we can eliminate the normalizing constant, we can equivalently say that we want to return the value of w that maximizes the joint likelihood of the data and the model variable, both of which we know. So again, I was able to get rid of this term previously because it didn't actually impact the location of the maximum. Okay, so last time we saw that we could find the MAP solution using Bayes' rule and using the posterior, where we find the point of the vector w that maximizes the posterior. So equivalently, the point of the vector w that maximizes the log of the posterior. And that solution was the same as the vector w that maximizes the log of the likelihood plus the log of the prior. In other words, the log of the joint likelihood, because the product of the likelihood and the prior is the joint likelihood. When we solved this for the linear regression problem, we saw that the MAP solution was equal to this, which corresponded to the ridge regression solution, where we've made a redefinition of that regularization parameter. Okay, so this brings us to the difference of point estimates for model variables and Bayesian inference. So point estimates, what we mean when we say we find a point estimate is that we find a specific value for an unknown model parameter according to some inference or inference procedure. So for example, the MAP solution and the maximum likelihood solution, corresponding to ridge regression and least squares, are both point estimates because they return specific values of the unknown model variable w. So Bayesian inference, instead of returning a point estimate, is going to try to define or return a probability distribution on the unknown model variable, in this case w, given the data. So Bayesian inference, instead of returning a specific w, is going to return a distribution on w. So let's look at Bayes' rule and the linear regression problem that we've been discussing thus far. So since w is a continuous valued random variable in Rd, Bayes' rule says that the posterior distribution of w given data y and x, so that's what this is, the posterior probability of w given data, is equal to the likelihood of the data times the prior on w, divided by the normalizing constant, which is the integral of the numerator over all possible values that w can take. So that is, we get an updated distribution on w through the transition of prior to likelihood to posterior. Or in other words, we would say the posterior probability of something is proportional to the likelihood times the prior. So let's see how we can do fully Bayesian inference for the linear regression problem. So again, we're going to work with the proportionality. So the posterior distribution of our regression coefficient vector w given the data is proportional to the likelihood of the responses given w and given the covariates x times the prior of the regression coefficient vector w. We've defined the likelihood to be a Gaussian, a multivariate Gaussian with this form, and the prior to be a zero mean Gaussian with this form, where again, because we're only working with proportions, we can eliminate anything that pre-multiplies this function that doesn't involve w. So we've removed some terms here in the proportionality. And then if we multiply this thing through, we can equivalently say that the posterior is proportional to this term. So what have I done here? I've actually expanded this into the three terms that result from taking this dot product. I then brought this term over into this exponential to have one exponential term. And then I've reorganized some things so that we can write it as a quadratic of w, where this term results from the prior and this term results from the likelihood, as well as this additional term here. And then the term that involves y transpose y, again, I've removed that because that's simply equal to a pre-multiplication by this value. And so when we normalize this, when we divide by the numerator integrated over w, this will simply cancel out. So again, we take advantage of the proportionality that we're working with to remove terms that aren't necessary.